So if we have turbulent turbulent pipe flow and high wall roughness, we must I teach you that if we have a laminar flow, we have to calculate a lambda value to calculate pressure drops and energy losses over long pipe systems. But if you have turbulent flow, we need and we have a high wall roughness, we need a more sophisticated formulation. Here again is a small picture of a hydraulic smooth wall, rough wall, and a hydraulically rough wall. And we have our flow region, we have our turbulent core, and we have, if we have this high roughness, we have like hills and valleys, and also the boundary layer has to follow this wall structure. Okay, and so we must add an additional formulation to our law. Please also refer again to the formulation of the Bernoulli law, where this additional pressure drop term was added. It was rho times J, and you already know these Chi values. You have to add the Chi values by the different armatures, but now we have this additional lambda value, and we multiply it with the length of the pipe divided by the diameter, and then we can add an additional term for pressure losses over the length. And now how can we estimate this lambda to fulfill the calculation? This is quite tough. It's also a measured value, and here we go. We need this, I called it Nicorazzi diagram. You can also call it Moody diagram. Again, we have here two different scientists who made the same measurements. And if we take this Moody diagram, we have here again our Reynolds number. Please remember, it is calculated by diameter times velocity times acoustic length scale divided by viscosity. And we can, and please also remember, if we are lower 2320 in the Randstone, we have a laminar region, and then we are here at the beginning of the diagram. Here is this laminar region, and take care, the x-axis is a logarithmic length scale, and always if you have this logarithmic length scales and diagrams, it's a little bit dangerous. You can, it's like it's a bit, you can look really closely at the beginning. You have really detailed results at the beginning, but you can also look really far. You have really good detailed results at high numbers. Yeah? You can look at small numbers really detailed, and you can look at high numbers really detailed. That's a big advantage of logarithmic diagrams. And now we can look at our lambda value. We can look at our small Reynolds numbers, and in the laminar region we don't have any effect of wall roughness on the lambda value, and we can just, it's an easy line. It's we can look up for our lambda, and then we can take it. But if the flow gets turbulent, if we get higher Reynolds numbers, then we will have for every different roughness different lambda values. So here we see this a lot of different lines, and this is the sand grain roughness divided by diameter of the pipe. And for example, here if you have a really small diameter and high roughness, you have really high lambda values, or if you have really high diameters and small roughness, you will get small values. So that's the Moody diagram, And if you want to make your exercise calculation, just go into the Moody diagram, calculate the Reynolds number for your pipe, look at the lambda value, and then I go back to this slide, and then you enter your lambda here, and then you can calculate the pressure drop. Okay. There also, if you now ask me how can I calculate the roughness, of course you can measure it. You can go with a small ruler to the pipe and measure it, but you can also look into some tables, and here are some different pipe roughnesses are sampled. You can look them up. You can look at the different roughness values in millimeters, for example concrete or metal or copper, and you can look them up. Okay, here's also another small explanation of an elbow, how the turbulence is built. And I teach you that we always have turbulent region after this elbow, inside the elbow, and additionally you induce in this flow field a swirl. Yeah, the water inside the pipe will be faster at the walls, and it will cause a swirl, and that's also a law of fluid dynamics. You will never have one single swirl. If you have swirls, you always have two different swirls. Yeah, you have always this. It always looks a bit like you could call it like a mushroom. You always will have one high flow region in the middle, and then two swirls at the side. Okay. Now, if you want to calculate different terms for the lambda, you just sum them up over the whole pipe. You have to collect them, you have to sum all the lambdas together for the special lengths, you have to sum up all the sheaths for the special lengths, and then you can calculate your pressure drop. And also, if we have here a complicated system, we have here a tank and a tank at the top, and now maybe you can try to formulate a Bernoulli's law for the whole pipe system. You can measure all the different lengths, multiply it with lambda. You can look where you have your armatures, you need then characteristic G values, and you can go through your pipe, sum all the pressure drops up, add it to Bernoulli's law, and then you get a full energy balance for the whole pipe system. And you can calculate, for example, how big your pump must be, how much pressure your pump must deliver to transport the flow. Okay, so I think that was the last slide, and in the exercise we also want to do some exercises for the pipe system, and you should have a look at our learning control. Now we learned a lot. We learned something about cavitation, we learned something about pressure drops, we learned something about turbulence. So I think we had a lot of pretty interesting stuff in this lecture. Also all the stuff you need to solve your exercise. And here's a learning control. So let's have a look. How can pressure change in fittings or armatures of pipe? You get high pressures or low pressures because of the fittings. How does fluid flow behave if a pipe gets smaller? Yeah? What changes if you get smaller diameters? And you can describe the outflow of the tank and the nozzle. You must be able to calculate the pipe system. You must be able to explain the effect of cavitation. That's something we can't calculate so much in the exercise here, it's this cavitation effect, but you have to understand it. That's important for me. You want to build up good pipe system, if you want to build up good pipe, you have to understand that cavitation can occur. Yeah, and where will it occur? That's important. You must know what the Reynolds number is. This is something, if you work in fluid dynamics, if you know fluid dynamics, if you want to be a scientist in fluid dynamics, or if you want to be an engineer who builds up fluid dynamic systems, you must know what the Reynolds number is. You must know that you can calculate with the Reynolds number if a fluid is turbulent or if a fluid is laminar. You should know what the Nicorazzi or Moody diagram is. You should know how you can use the Moody diagram to solve your pressure drop problems. You must know how to that you have to look at the Reynolds number in the x-axis and go to the right line, and then you get your lambda values. Okay, you must be able to calculate hydraulic diameters. Calculation of the hydraulic diameters of a round system is really pretty cool. You just take the diameter of the round, of the circle, but if your geometry gets a bit more complicated, you do not have to know it for triangular geometries. That's not necessary. I told you I've never seen a triangular pipe. Maybe I have to look it up, but it can occur that you have rectangular pipes, and if you have a rectangle, I would say you can have rectangular pipe systems for gas flows, but I would say you will nearly never have rectangular pipe systems for liquid flows because of the cavitational and erosion problems. But you must be able to calculate the diameter, and it's always 4 times the area of the rectangular divided by the surrounding. And you should also know how to solve an exercise if you have a rough surface. If you have, for example, a pipe system for wastewater made of concrete, you will have rough surfaces. Or if you have different metal types or copper types, you can have rough surfaces. Okay, that's it.